Okay, welcome to lecture here. We're continuing on with chapter 3, I believe. We'll get started here in just a second. Continuing on with nomenclature. Okay, so we've been talking about nomenclature, basically how to name things here. And last time we talked about ionic compounds, really, and sort of classified sometimes as type 1 or type 2 ionic compounds. And when we do have an ionic compound, as we sort of talked about, the difference there is in an ionic compound, it is always a metal and a non-metal together. And when we get a metal and non-metal together, whenever the combination of those two things come together, we always get a transfer of electrons from the metal to the non-metal. And what that creates is a cation, which is something that is positively charged, and an anion, which is negatively charged. And the cation comes from the metal and the loss of electrons, which is why it becomes positively charged. And the non-metal gains the electrons, becomes negatively charged. And there's absolutely no sharing of electrons that is occurring in an ionic compound. It is solely held together by that electrostatic attraction, the positive and negative attraction that occurs. In general, when we do have a cation by itself and we want to sort of name the cation by itself, something with a positive charge, when it is a metal, we simply use the entire name of the metal. So Na plus would be the sodium ion, Ca2 plus would be the calcium ion. It is the non-metal or the anion that does get the IDE at the end of the name. So we drop the last part of the non-metal name and we replace it with IDE. So something like O2 minus goes from oxygen to oxide. N3 minus goes from nitrogen to nitride, IDE. Chlorine goes from chlorine to chloride when it gains a -1 charge. Now, when we do basically put those two things together, our metal and non-metal, it's always the metal that is the most important sort of aspect of that. And the reason is the metal, if it contains a metal from group 1, 2, or 3, or if it is zinc, cadmium, or silver, what those all metals all have in common is that they have basically a fixed charge. So if you remember, we talked about that group 1 will always form a +1, group 2 will always form a +2 charge, group 3 will form a +3 charge, really aluminum. And then those transition metals of zinc, cadmium, and silver, sort of like a backwards L if you kind of head that way. Zinc and cadmium will always form a +2 charge no matter what the situation is, and silver there will form a +1 charge no matter what the situation is. So they all have fixed charges, and when you have a metal that has a fixed charge with a non-metal, that is sometimes referred to as a type 1 ionic compound, which basically means to name those guys, you simply just use the whole name of the metal and ID on the second part of the name, as we also talked about, regardless if there's two of them or anything like that. So if we had something like what we saw, I think last time, CaCl2, this is calcium chloride. Again, the 2 here has no effect on the name, and we just go calcium and chloride on the last part of the name. Again, no effect, no prefix or anything like that. The reason there is a 2 there, as we talked about, is whenever you put the positive and negative together, you want no charge equals 0 in the simplest way that you can do that. And since calcium is group 2, that means it has a +2 charge. Chloride is group 7, which means it has a -1 charge. So again, the reason the 2 is there so that we get a grand total of -2 to balance out the positive 2 that is there. But in terms of the name, it has really no effect on the name at all. And that leaves us another type of ionic compound where we do have, again, a metal and a nonmetal. And the major difference here is that the metal is basically a transition metal, are just to the right of the staircase there. So again, on the periodic table, our transition metals and our staircase that kind of comes down. And also over in this region where we have things like lead and tin and bismuth and antimony. So SN, SB, PB, BI. These guys, although they're not transition metals, they're basically named the same way. And basically they all have the variable charge. So in certain cases, they may be one charge. In other cases, they may be something different. So the way that we go about naming these guys, which are sometimes classified as type 2 ionic compounds, again, the metal being the important one here, that it is a transition metal, it has a variable type charge. We still use the whole name of the metal. We still do the IDE at the end of the non-metal. The only difference again here is we need to figure out what the charge is on the metal. So an example like we did last time, I think we had FeCl3. Again here, iron, if you looked at it, was in the transition metal region. Not sure what the charge is, but the good news is you will always know what the charge is on this guy, and that is group 7, which means it has a -1 charge, and there are 3 of them there, as we can see, which gives us a grand total of -3, which means in order to balance that out, the iron in this case has to be +3. And when we go to name this guy, we will do iron, Roman numeral 1, 2, and 3. Again, not how many metals you have, but the actual positive charge there is on one of the metals. And same idea as above, even though there is 3 of them here, has no effect on the name. It is just chloride at the end of it. So iron, Roman numeral 3, chloride. So that's basically what we just went over, is what's on this slide. Again, ionic compounds pretty much named the same way. Only difference is you need to tell the person that, hey, in this particular case, because something like iron can have multiple positive charges, in this particular case, we're talking about the iron that has a +3 charge. And that's why we do need the Roman numerals. Any questions on that type of naming that we talked about last time? All right, so I think you got a couple here, or a few here. Why don't you give it a go, see what you come up with in terms of these names, then we'll talk about it. Okay, let me take a look here. So it looks like got some answers coming in. So looking good, I think. So let's take a look and go through them. Again, when we look at this, we do have Mg, which is magnesium. We have Br, which is bromine. So that is a metal, non-metal. And again, as soon as you see metal, non-metal, you know it's an ionic compound. And again, it is that first guy, which is really the important. And that first one is magnesium. And what we know about magnesium is group 2, which means it always has a +2 charge, and a fixed charge, which means we just need to use the whole name there. So this is magnesium, and bromine becomes bromide, IDE at the end of it. Again, the 2 has no effect on the name, but the reason we do have the 2 is to balance out that charge. So our anion here would be Br minus. This guy here would be our cation formula. So if we had to write the formula for the cation, it would be magnesium +2. we had to write the formula for the anion, it would be Br minus. But when we do put them together, no charge. And again, this would be the proper name. So very good. We got LiO, again, Li being lithium, which is a metal. O is oxygen, which is a nonmetal. So again, an ionic compound. Again, here we see lithium, which is the important one. Lithium is group number 1, which means it is a type 1 compound because it has a fixed charge. It's always going to be +1. So again, we could just proceed to the name here. That is lithium, and this becomes oxide. Now, same thing here, even though there's 2 lithiums, has no effect on the name here. It's just lithium. And again, just oxide here. And no need for a Roman numeral here because lithium is our fixed cation there with a fixed charge. Our anion in this case would be O2 minus, and again, that is why we have not one of these lithiums, but we do have 2 of them to balance it out. And lastly here, Cr and F, and Cr is a metal, and F is a nonmetal. The key here, again, going to be our metal. Chromium is a transition metal. So automatically that should tell you this is a type 2 type guy, which basically means I have 1 chromium. I'm not sure what the charge is, but we do know that F, which is fluoride, is group 7, and there's not 1 of them in this case, but 2. It gives you a grand total of -2. So here our chromium will be 2, and that means that this should be chromium Roman numeral 2. Again, the Roman numeral for the actual charge that we got going on there. And fluorine becomes fluoride. So chromium, Roman numeral 2 fluoride. Again, no effect on this type of naming for that extra 2 that is there. Any questions on those names, or how to do type 1 or type 2? Okay. Here's sort of a decision tree based on sort of what we talked about. And again, really it is that metal, which is the important one there. And if it is a fixed charge, no Roman numerals. If it is a sort of variable charge, which is a transition metal, or just to the right below the staircase, then you do need the Roman numeral to indicate the charge. So let's talk about type 3 compounds. Type 3 compounds are a little bit different. They contain only nonmetals, which means they are going to be really covalent compounds, which means they are going to actually share electrons here. So different than when we get a metal and a nonmetal together, we get that transfer of electrons. When we actually get 2 nonmetals together, what we end up getting is sharing of those electrons. And we do have a different way of naming these guys. And I might have mentioned it last time as well, but people always want to do prefixes and all those type of things. And out of all the things, this is actually where you should do prefixes. So when we name these guys, we do sort of name it kind of similar. We use the whole name of the first element in the formula. We also use the second name like a normal nonmetal, which means it drops the last part and it gets an IDE. And the difference here is we actually do use some prefixes when we go to name these guys. Prefixes like mono, which is 1, di, which is 2, tri, which is 3, tetra, which is 4, penta, which is 5, hexa, which is 6, hepta, which is 7, octa, which is 8, nona, which is 9, and our good friend deca here, which is 10. And as we will see, this is actually the situation where you want to use prefixes, not anywhere else. And these are really the easiest ones. You pretty much just need to pick the right prefix and whole name and IDE on the second name. There are a couple of rules here that we'll talk about. One major rule is we do not use mono on the first name, but we can use it on the second name. So the only prefix that is not used on the first name is our mono, but definitely we could use it on the second name. And the other thing that happens when we do use these prefixes is sometimes we do get a couple of vowels that sort of back up to each other. So from the prefix, for example, we'll sometimes get like an A and an O that will back up. A being from the prefix, O being from the first letter of the next element. So usually we get rid of the A. We also will sometimes get a couple of O's that will sort of back up to each other. Again, the first O from the prefix at the end, the second O from the letter of the first element there coming next. So we typically will get rid of that. So again, if we had monoxide, that would be basically one oxygen. We do drop one of the O's there off of the prefix, and it really is monoxide rather than monoxide. So that's a very common sort of one that we do. Actually, two I's seem to be okay. So you could go two I's to each other, I and I, but A and O is a common one. We want to get rid of the A in the prefix, and O and O, getting rid of the O in the prefix as well. These are, as I might have mentioned last time, just when we were talking about it, these really are the easiest out of all of them, but they are the ones that people definitely kind of screw up on the most because they try to do all kinds of things they shouldn't. They try to balance charges and all these things. And really, once you see non-metal, you should be really happy because really you just need to count what's there, pick the appropriate prefix, fix any type of vowel situation that's happening, and you pretty much can just write the name. These literally should take you like, a second to do when you see them because you really don't have to calculate anything other than choose the right prefix and put them together. So there's the table there. And here's what I was talking about just a second ago. Again, tetraoxide would mean we have 4 oxygens. We would typically drop the A off of the tetra part and be left with just the O. Same thing with the monoxide there, dropping off one of the O's off of the prefix. There are some non-metals that have common names that we talked about before. So here's 2 of the ones we talked about earlier. H2O is water, NH3 should be called ammonia, and CH4 is methane, which is, again, the simplest organic guide that you could have. And that is also a name that you should use. Yeah, so oddly, usually the 2 I's are okay. So that's what I mean. And that's exactly an example there. We have like di and iodine. So the II is actually okay in most cases on that. So that's usually okay. So it's usually the A and the O and the O and the O, but oddly the I and the I seems to be okay and acceptable in terms of the 2 vowels together. Other questions on that? All right. So you got a couple here. Why don't you give these guys a go, see what you come up with, and then I'll also give you some names. You could try to write those as well. So let's do trinitrogen. Hexoxide. Let's do carbon tetrachloride. Let's do disulfur pentasulf, not pentasulfide, that won't be good. Pentanitride. All right, so one's on the left there. Let's go with names. One's on the right. Let's go with formulas. See what you come up with. Okay, so let's take a look and see how we're doing. I see some answers rolling in there, so it's looking good, I think. So again, the way you want to approach this is when you see I, that is iodine, which is a nonmetal. You got O, which is also a nonmetal. So right there, you should be really happy because, as I might have mentioned, you don't have to worry about balancing anything or charges or anything like that. You pretty much just need to pick the right prefix. So 2 is di. So this is going to be diiodine. Again, whole name of that first element. So we got something like diiodine. And the prefix for 7 is hepta. And we will drop that A off of the prefix so we don't get the A and the O. Again, here, the 2 I's are okay in this case. You don't necessarily need the dash like I see in some of them. It's actually okay in this particular case. Same thing here. If we come to the next one, we got C, which is carbon, which is a nonmetal, O, which is oxygen, which is a nonmetal. Again, we're just going to pick the right prefix. So nothing written there is 1, and that means mono for the prefix. But again, we do not use mono on the first name. So we would not use the mono here and just use carbon. And the 2 prefix is di, and oxygen becomes oxide. So that is carbon dioxide. Coming down this way here, we got phosphorus, which is a nonmetal. We got Cl, which is a nonmetal. Again, nothing written there, so assumed to be 1. Prefix, again, going to be mono. But just like the previous one here, we will not use that on the first name. So that's phosphorus, whole name. And 3 is tri. And chlorine becomes chloride. So that is phosphorus trichloride. Any questions on those 3 names there? Okay. Now, when you are given sort of a name and you want to write the formula, yes, the names do need to be separated. So there is a space right here between them, if that's what you're asking. It may not look like a big space, but there should be a space between the first name and the second name, if that's what you're asking. Other questions on that? Okay, so when we do see the name, we do see the prefix, because again, don't have to balance anything. Pretty much just need to write what it says. So tri is the prefix for 3, nitrogen is N, so you just write N and a 3. Hexa is really the prefix for 6, oxide is oxygen, so O6 would be the formula here. Carbon, no prefix, but tetra on this one. Carbon nonmetal, chlorine nonmetal. So with no prefix on the first one, we know that there's just 1, and that would be just C. Tetra is 4, so Cl4, CCl4. And lastly here, disulfur penta nitride. So di is 2, and penta is 5, and nitride is nitrogen. And we get something like S2N5. Any questions on type 3? Again, type 3, relatively easy ones, but ones that people very often will sort of separate out the name incorrectly. They are different, besides the fact that I sort of made it up, but the first name, but they are technically different compounds. They are related to each other. So something we don't talk about really in this class, but those 2 guys are related to each other. They're related to each other by what's known as, one's like an empirical formula and one's a molecular formula. So NO2 would be considered what's known as the empirical formula, which is basically just the simplest whole number ratio what's present, while N3O6 would be kind of what's sometimes referred to as the molecular formula, which tells you exactly what's present. So they actually can be different things, and they probably are different things, but they are related to each other in that sense. They're basically whole number ratios of each other, and one's sometimes referred to as the empirical form, one's referred to as the molecular formula. Other questions on that? Now, one thing that involves sort of a non-metal and non-metal, which is sort of handled a little bit different than sort of type 3, is when we actually do have hydrogen involved. And when we do have hydrogen involved, actually, I'll just, here's a review of those guys. I'll just kind of put it here. So for example, let's say we had HCl. Even though H is a nonmetal, Cl is a nonmetal, we really don't typically use prefixes when hydrogen's involved. We almost treat it more like an ionic compound, and this is thought of as being H plus and Cl minus. Again, hydrogen has some different properties. So if we were to name something that's HCl, we would simply just use hydrogen and chloride. It's almost named like a type 1 compound when hydrogen is H plus and comes first. Has a little bit to do with it being an acid and that type of stuff. So for example, if you had H2S, even though again there's two of them here, we would just call this hydrogen sulfide. So when you have H in this situation, when it comes first in front of a nonmetal, it's almost thought of as being H plus as the cation. And then obviously the other guy being our negative anion in that particular case. And it's really almost named like a type 1 compound, regardless of how many hydrogens you have. That's sort of how you would go about naming it. So anything involves hydrogen in front with a nonmetal, this is always going to be the cation. And that's the way you could kind of do it. Yeah, exactly. You'd actually, and it's just kind of special with hydrogen. You wouldn't use dye or anything like that. You would just call it hydrogen sulfide. This is what is known as hydrogen sulfide gas. This is known as hydrogen chloride gas. And when they become acids, for example, HCl, this is known as hydrochloric acid. And that's really why it has a lot to do with the H being really in solution and stuff, H plus. So it's kind of like a weird name that when hydrogen's a cation, even though technically speaking, they're both nonmetals. And when we talk about bonding, they're actually sharing electrons. It's almost treated like an ionic compound, and it has more to do with hydrogen being sort of present. Hydrogen has some interesting sort of properties. So that's the sort of approach if you had something with hydrogen. Again, if you had HBr, you wouldn't call this hydrogen monobromide or anything like that. This again just would be hydrogen bromide. So almost treated just like a type 1 sort of compound, and that's sort of how it usually is sort of treated when you have that H that comes first. So here's sort of the review of those three different types of naming that we talked about. Type 1, again, metal, non-metal, metal important, going to have a fixed charge, so no Roman numeral needed, whole name of metal, IDE on the non-metal. Type 2, also ionic compound, metal, non-metal, metal also the important one here. Metal is a transition metal, or just to the right, has a variable charge, which means whole name of the metal, Roman numeral for the charge on the metal, just one of the metals by themselves, and IDE at the end of it. And type 3 is our non-metal sharing of electrons, covalent compounds, and that is where you use prefixes. So we do not mix that anywhere. There's no in any of these examples where you see the use of Roman numerals and prefixes together, because, well, that's just wrong, and you should put an X on that yourself if you do that. So don't do that. So prefixes only with nonmetals, Roman numerals only with metals and nonmetals, where the metal is a transition metal. And again, no real mixing of those two. So again, you find yourself with Roman numerals and prefixes in the name, that's sort of a binary compound where there's just two elements involved, probably going to be wrong in terms of the name. Any questions on those type of naming? And it's just a decision tree based on what we talked about. So the final kind of type of name we're going to talk about are polyatomic ions. And polyatomic ions are really groups of nonmetals that are together. And these groups of nonmetals that are together have a specific formula, and they have a specific charge. So when we look at something like this, NH4NO3, this is actually two polyatomic ions together. I'll just kind of draw it like this. And we would break it apart right about here. And the guy on the left is actually NH4 plus. And what that means is this one nitrogen and that 4 hydrogens. They're all bonded together, and they're actually bonded together by sharing of electrons, which means they never break apart. So this 1 nitrogen will never come off by itself, and the 4 hydrogens, if they move around, they move around as a whole unit, and the entire unit has a +1 charge. This has a special name, which is known as the ammonium ion, not to be confused with NH3, which has no charge, 1 less hydrogen, and known as ammonia. So ammonium is an ion with a charge. Ammonia is no charge and only 3 hydrogens and 1 nitrogen. This guy is also a polyatomic ion. This is 1 nitrogen that is sharing electrons with 3 oxygens. All those guys move around together, and they all stay together, never break apart from each other, and it has a -1 charge. And this is what is known as the nitrate ion. Now, ultimately, these are 2 ions that are together. This is our cation, which is our positively charged guy. This is our anion, which is our negatively charged ion. And ultimately, it's the same thing that we talked about really with type 1 and type 2. When we put something that's positive and negative together, we want no charge, which means this is +1, this is -1. So that is why when we put them together, we actually just need 1 of each of those. And that basically means we have 1 ammonium at +1. We have 1 nitrate at -1. +1 -1 gives us 0. And to name this, we essentially just put these names together. So putting them together, this guy here would be known as ammonium nitrate. So polyatomic ions are really groups of nonmetals, and for the most part, this is like the only positive polyatomic ion that you'll come across. Pretty much all the other polyatomic ions are negative, which means when we do sort of name these guys or use these guys in sort of words and stuff like that, our formulas, they really will basically be named like a type 1 or type 2 compound, which means they typically will be hooked up with a metal. So either that metal will be a type 1 or a type 2 metal, which means either you'll need Roman numerals or you will not need Roman numerals. And it's really depending on the metal. The name of the polyatomic ions, you do need to memorize the name and the formula. So I think we got a table coming here. Here's a table from your book of some polyatomic ions. And you really just need to memorize these guys, their name, their formula, and their charge to be able to put them together correctly. There is a way that you could do that. And a way you could do that is there are things that are related to each other. So if we look at these 2 guys here, that is NO3 minus and NO2 minus. That NO3, like we were just talking about, has a -1 charge. Everybody stays together. That 1 nitrogen, 2 oxygens all stay together and has a -1 charge. The only difference between these is the number of oxygens. And one has nitrate and one is nitrite. You do need to kind of memorize this table, and I think there will be one up on Canvas as well. So you'll need to kind of know definitely these tables, and it'll say specifically which ones you need to know as well for sure. But you probably need to know these. Yeah, this will be on exam 1. So this is nitrate and nitrite, and that is ATE and ITE. If you look over here, another sort of combination is SO4 2 minus, and this is 1 sulfur and 4 oxygens together. This is known as sulfate, ATE. SO3 2 minus is one that's related to it, and that is 1 sulfur and 3 oxygens. This is known as sulfite, ITE. And in a group of 2, there will be basically one that has more oxygens. The one that has more oxygens ends in 8. A good way to remember is like you ate too much. So the one with the most oxygens is 8. The one with the least number of oxygens is 8. There's also, when you look at a table, and this is sort of a partial table, but another table, there's also ones that are groups of 4 that are related to each other. And the most common group of 4 are ClO4 minus, ClO3 minus, ClO2 minus, and ClO minus. All these guys have a -1 charge. Everything that I'm boxing stays together. They're all sharing electrons, not going to break apart. They all have a -1 charge. So really the only thing that is different between all these guys is the number of oxygens. So you could kind of take the same approach if you break it right about here. Everybody to the right has the least number of oxygens. So this guy right here is chlorite. They should end in ite. This guy on the right is also chlorite. So clearly you can't have the same name for two different things. So when you have a group of four, the one with the least number of oxygens ends in ite, but also starts with hypo. So this is what is known as hypochlorite. Chlorite is next to it. These two over here on the left in this group of four have the most oxygen. So this guy would be known as chlorate, ATE. This guy would also be known as chlorate. But again, you can't have the same name for two different things. So in a group of four, the one that has the most oxygens will also start with per. So this is perchlorate, chlorate, chlorite, and hypochlorite. That is a very common group of four that you come across. Cl is a halogen. You actually can replace the Cl with anybody in that halogen. It will name the same way. So for example, if I went with BrO3 minus, instead of chlorate, this would become bromate. So kind of named the same way. So you can kind of swap that halogen out for any of those. So that's a very common thing that you can kind of see on the thing. The other common thing that happens with these polyatomic ions is, for example, right here, we have CO3 2 minus, which is carbonate. And sometimes we put an H plus in front of it. And when we put an H plus in front of it, it becomes HCO3 minus. And if you just follow what happened there, we put an H onto this. So that's HCO3 plus 1 and -2 leaves us a -2. We basically put a hydrogen in front of it. So the name now becomes hydrogen carbonate. Or instead of hydrogen, sometimes people will use bi. So this is known as bicarbonate. Same thing. So that's a very common sort of difference. The hypo here, the question is where the hypo comes from. That is for when you have a group of four polyatomic ions that are related to each other. The one with the least number of oxygens out of that group of four will start with hypo and end with ite. So hypo means kind of less than, so it has less oxygen than everybody else there. And that's why in a group of four here, the one with the most oxygens will start with per. So per basically is sort of for the one that has the most oxygens in a group of four. So bicarbonate, hydrogen carbonate, very common. You see that down here. If you put an H plus in front of the sulfate, you get hydrogen sulfate or bisulfate. So again, same idea. You can use either name, is fine. Some people use bi, some people use hydrogen, and it's still very common that people use bi instead of hydrogen, especially with like bicarbonate. So sodium bicarbonate, you probably heard of. Again, that's still a very common sort of name that's used very commonly with these. As you can kind of see here, for the most part, everybody ends in ATE or ITE, but there are some polyatomic ions that end in IDE. So CN minus is cyanide, IDE. OH minus is hydroxide, IDE, but most of them will end in either ATE or ITE. And like I said, as you can see here, a majority of them are negatively charged, which means when they are hooked up, they typically will hook up with our metals. So you really can follow type 1 or type 2, which means either it will need a a Roman numeral or no Roman numeral. Here's another sort of chart that has some of the other ones on there as well. So you can review this one as well. But here's that group of four, as you see here. This will be it'll be in the lecture notes on the recording, so you could go back and review it if you like. And I think I'll post up on Canvas an additional sort of polyatomic ion table for you that has some of these kind of together. Okay. So let's take a look at, these are again, some of those patterns that I was just talking about where you can have a group of 4, and again, in a group of 4 that's related to each other, really the only thing that will be different is the number of oxygens, and that's where we get our per and our hypo inserted in there. Again, the ending part will kind of be the same like I did on that one. You kind of split it off. The 2 with the least should end in 8, 2 with the most should end in 8, and again, the appropriate sort of prefix at the beginning of the one with the most and the one with the least number of oxygen. And that's what I also said. Again, you could substitute out in something like chloride. If you just put Br in there, it becomes bromate. If you had I in there, like IO3 minus, it would be iodate. So it's named very much like it. And again, if you add an H plus in front of one of those polyatomic ions, you put hydrogen in front of it, or again, that is where they sometimes will use bi instead of hydrogen. As we see here, again, hydrogen carbonate and bicarbonate, same thing, HCO3 minus. And a reminder that you're not just putting the H in front here, but the H also has the plus, which affects the overall charge. And again, that's how we get down to -1 as we go +1, and -2 leaves us a -1 that's left over. All right, so let's see here. Let's try some here and see what you come up with. So why don't you do some names for some of these and see what you come up with. And do some names here. All right, so why don't you give the names on the left of these sort of polyatomic ions, and on the right there, let's give the right formula. It's got copper 2 nitrate, nitrite, I'm sorry, and barium hydrogen carbonate. See what you come up with. Take a couple minutes, see what you come up. And we'll add one more. Let's do ammonium. Let's do ammonium phosphide. So again, as you approach these, you want to approach them really kind of the same way as type 1, type 2, and sort of work it out that way. See what you come up with. And again, obviously use the table, since you haven't learned them yet, to help you along. Okay, so let's take a look, see some answers rolling in there, see how we did. So again, you really do want to kind of approach this the same way as everything else. So you kind of want to identify what you got going. So sodium is a metal. Once you hopefully get those polyatomic ions under control, CO3 is CO3 2 minus, which is one of those polyatomic ions. So again, once you have a metal and a polyatomic ion together, we would split it right about there. Again, if you have a metal, it's always the important guy. So when we see sodium, we know that's group 1. So it's really like a type 1, which means we don't have to worry about Roman numerals or anything like that. So we would just call it sodium. Very badly written there, sodium. And again, our CO3 here is CO3 2 minus, and that is carbonate. So this would be sodium carbonate. Now, the reason we do have 2 of the sodiums is sodium is +1, and we need 2 of them to balance out the -2 charge from that polyatomic ion. Again, +2, -2, when we put them together, gives us the formula that we started with and no charge overall. But again, because it's really hooked up with this metal, just like with type 1, just use the whole name of the metal and the whole name of the polyatomic ion that you can find on that table. So this first guy would be sodium carbonate. And just like what we did with type 1, even though there's 2 of them here, no effect on the name, so no prefixes on that sodium, just like we did with type 1. Coming here, if we look at CaOH2, we have again calcium, which is a metal, and OH, again, we will hopefully be able to recognize that as a polyatomic ion, which is OH minus. And that's an oxygen and a hydrogen together with a -1 charge. And there's 2 of them. And the reason there is 2 of them is calcium is group number 2 and has a +2 charge. So +2 and -2, when you add those together, gives us 0. So same idea here. The metal is the important one. That's a type 1 metal. So this is going to be calcium. And again, we just use the whole name of the polyatomic ion, which is hydroxide. Just like everything else, no effect on the name here, the 2 of them. Again, no prefix or anything like that. And this would be calcium hydroxide. Now, we do see parentheses around this. And the reason that we have parentheses around that is what we are trying to say is we have 2 of the OH minuses. So whenever you have more than one polyatomic ion, you do need to put parentheses around it and the number on the bottom, because if you just wrote CaOH2, what that implies is you have 2 hydrogens and 1 oxygen, which is really not what you're trying to do, because here what you really are saying is I have 2 oxygens and 2 hydrogens. So we always, when we have more than one polyatomic ion, you need to put parentheses around it and the number on the bottom here. So again, that's why the parentheses are there. Lastly, here we go Fe, which is iron, which is a metal. SO4 is sulfate, SO4 2 minus. Iron is a transition metal, which means we do need a Roman numeral, and we do need to figure out the same way. So in this case, we have 3 sulfates. And again, if you just draw it out and count up the charge, 2, 4, 6, that is -6. We actually have 2 irons in this case. What that means is I have 1 iron there and another iron. And in order to balance that out, each of these irons has to be +3. +3 and +3 gives us +6 overall to balance out the -6 charge. And that's how we do get to this formula. Again, parentheses around the polyatomic ion with the number on the bottom. So this would be iron Roman numeral 3 for the charge. And even though we have 3 of the sulfates, we just use the last name there, or the whole name of the polyatomic ion. And this would be iron Roman numeral 3 sulfate. And it is 2 words. I didn't space it out very well, but it is 2 words there. Question on the names of these 3 guys. Now, when we do have the name and we want the formula, we want to work our way backwards like we sort of done before. So copper Roman numeral 2 automatically tells me I have a copper with a +2 charge. Nitrite is one of those polyatomic ions from that table. And if you look at it, it is NO2 minus. So again, that 1 nitrogen, 2 oxygens all stays together. When we put this together, we want no charge. So what that tells us is we do need 2 of these guys to balance it out. So that means the formula should be Cu parentheses NO2, Na2 on the bottom. Again, we have 2 of those NO2 minuses, so we do need the 2 on the bottom there to balance it out. And here we have barium hydrogen carbonate. So same idea, barium is group 2, so we know barium is +2. Hydrogen carbonate is the same as bicarbonate, and that is from the table HCO3 minus. So same idea here, +2 and -1 means we actually need 2 of these guys. So we are going to need some parentheses around that. And we are going to need 2 of them to balance it out. Question on that particular one there. And lastly here, ammonium, which is not NH3, but that is NH4+. So remember, NH3 is ammonia, no charge. NH4+ is a polyatomic ion. And phosphide is phosphorus off the periodic table, group number 5, which means it has a -3 charge. So actually need 3 of the NH4 pluses to balance it out. So we are going to need parentheses around that polyatomic ion. And 1 of those phosphorus there. And we will look something like that. Any questions on polyatomic ions? Really important, again, to know the formula, the name, and more importantly, the charge, because probably in most cases it will be hooked up with a metal, and it's ultimately an ionic compound, so you need to be able to balance it out to 0. Any questions on any of that naming there? Okay. That is all the naming we're going to talk about, so you now should know how to name everything, hopefully. Type 1, type 2, and type 3 guys, and our polyatomic guys. Any questions on naming before we talk about bonding? Okay. All right, then let's talk about bonding. And we do show bonding using Lewis dot symbols, and these are sometimes what are referred to as electron dot symbols. So electron dot symbols, Lewis dot symbols, kind of the same thing. And when we do that, it's really, when we talk about bonding, it's only really the outermost electrons, which are those valence electrons. And a reminder that the valence electrons you get from the electron configuration, or you could get from the group number on the periodic table. So everybody in group 1 has 1 valence electron, 2 valence electrons, 3, 4, 5, 6, 7, and 8 valence electrons. So the number of valence electrons equals the group number on the periodic table, and that's probably the easiest way to do it rather than write the electron configuration. And when we do a Lewis dot symbol or electron dot symbol, it is the symbol represented here by X. And really, the only rule is really no more than 2 electrons per side. That's usually the rule. So if you do 2 electrons per side, you max out at a grand total of 8 electrons. And 8 is a very important number in terms of bonding. It is what is known as the octet rule. And we'll see more about that a little bit later on. But for the most part, most people kind of, kind of go around and then, kind of go back and pair up. Doesn't really matter, to be honest with you. The really only major rule is no more than 2 per side when you put those dots. Each of these dots represent the number of valence electrons, not the total number of electrons that are there. So remember that the valence electrons are the outermost electrons and the ones that are involved in bonding. So we can use a Lewis dot symbol, which again basically consists of the symbol plus a dot for 1 of the valence electrons there. And here's sort of an example of all those things. So again, you can see everybody in group 1 has 1 dot, represents as 1 valence electron. Everybody in group 2 has 2 dots for his 2 valence electrons. And then continuing on here, 3, 4, 5, 6, 7, and 8. Helium, which is part of group 8, doesn't have 8 valence electrons. And that's because helium only has 2 total electrons. So it can't have 8 if it only has 2 maximum. but everybody else there, when you get to group 8, will have 8 valence electrons. So this is what our electron dot symbols or Lewis dot symbols look like, and we could use these guys to help us understand bonding and what's happening with bonding. And we could use them really to understand two types of compounds. One is an ionic compound and one's a covalent compound. And we talked about this with naming. Again, an ionic compound is our metal and nonmetal. And this is our guy where there is a transfer of electrons, no sharing of electrons. It is just the positive, negative attraction that holds that together. And that is what is known as the electrostatic attraction. And that's different than our covalent guy, which is like type 3 guys we've been talking about. That's when our two nonmetals come together. And here we do have sharing of electrons. So that is the major difference between those two. And what helps us sort of understand that is when we talk about sort of these periodic trends on the periodic table, if you think about where nonmetals are located, nonmetals upper right, which means when nonmetals and nonmetals get together, they share very similar trends in terms of, I want to hold on to electrons, I want to gain electrons. So the best they could do when they get together, two nonmetals, is to share electrons. While when we get a metal and a nonmetal together, they're on like opposite ends of the periodic table. And because they're on opposite ends of the periodic table, metals are guys that pretty much want to get rid of their electrons. Nonmetals are ones that really want to hang on to their electrons and actually pick up electrons. So that's why we get that transfer of electrons when those two get together, rather than when two nonmetals get together, they pretty much, stay together and will share electrons rather than transfer electrons. And that generally tells us that our cations will be our metals, group 1 and 2, far left of the periodic table, and our nonmetals, upper right, will be our anions in an ionic compound. So let's take a look at actually what happens when two things come together, like a metal and a nonmetal come together. So this is our lithium and our fluoride, and lithium's electron configuration 1s2, 2s2, 1s2, 2s1. And fluorine 1s2, 2s2, 2p5. This is the valence electron here for lithium. It is group 1, so it has 1 valence electron. This is the 7 valence electrons for our fluorine, also group 7, so it has 7 valence electrons, which would be these two. So if we were to draw sort of what's happening here, lithium would be drawn with 1 valence electron, like so, having that electron configuration 1s2, 2s1. And fluorine would be drawn with 7 valence electrons, having that electron configuration of 1s2, 2s2, 2p5. And what's going to happen here, because this is a metal and a nonmetal, when they do get together, we are going to get that transfer of electrons from our lithium to our fluorine. And it's at that point when the lithium gives up its electron to fluorine, that is when the lithium becomes positively charged. The fluorine then picks up that electron. And when it picks up that electron, that is when the fluorine becomes negatively charged, like so. In terms of transition metals for lecture, you don't really have to worry too much about it. In terms of valence electrons, some people will say they have 2 valence electrons because when they do lose electrons, it's actually the s electrons they lose first. Some people will say they could have upwards of 12 because technically they also have the d electrons involved, which can be like 10 electrons as well. I personally, a lot of people will go with 2 because those are really the first ones that are lost. But some people could say, depending on which one, it could have upwards of 12 because you could technically divvy into the S and then the D's and stuff like that. You don't really have to worry too much about transition metals for us in terms of bonding and stuff like that. But essentially, if you did iron, it would be argon 4s2 and 3d6 would be the electron configuration for argon. Now, what happens when iron does lose electrons is actually these guys get lost first. And that happens for all the transition metals. And that's why some people will say it has 2 valence electrons. But if it needs more, it will then go into the Ds. So some people will say, you know, something like iron could have upwards of 8 valence electrons, the Ds included, and stuff like that. And it's just kind of a weird thing that happens in transition metals. But some people will stick to kind of the 2. Some people will say they can have upwards of 12, depending on which one you're talking about. And again, because they will lose these S's first, and then they'll go into here next. And so for example, iron with a +2, like I think we might have talked about, argon 3d6. Iron with a +3 charge, argon 3d5. So you can see it jumped into the D's at that point and stuff like that. So I would go with 2. You might want to ask your lab instructor what she thinks. Again, I've seen people say 2 to 12, depending on sort of what to talk about. For us, in terms of lecture, you will not have anything to do with transition metals and sort of valence electrons or bonding or anything with that. So it will just be those representative numbers for lecture, so you don't have to worry about it. All right, so this is essentially what happens, and we do need to include the charges here when we draw that. So fluorine has 7 valence electrons because it's in group 7, but essentially these 2 electrons here are on the first energy level. This is the second energy level. That's what the 2's represent, and there's 2 electrons there and 5 more there, which would be the 7 valence electrons. So the valence electrons are the outermost highest energy level. In the case of fluorine, there's 2 electrons in the s orbital on the second energy level, excuse me, and there's 2 electrons in the p subshell on that second energy level. So the 5 and the 2 is how you get to 7. The easier way of doing that is just to look on the periodic table, and fluorine is in group number 7, which means it has 7 valence electrons. So that's definitely the easier way to do it. So we do want to include the charges here because that indicates that none of these electrons are being shared. And what holds this together is that positive charge here and the negative charge here. You can, if it says don't, as long as it doesn't say don't use the noble gas configuration, you can do that. So when we look at what happens in terms of the electron configuration, the lithium is going to lose this 1 electron. So lithium with a +1 charge only has 2 electrons, which has an electron configuration of 1s2, or that is the same electron configuration as helium. Fluorine will pick up the electron right there, and it will end up with 1s2, 2s2, 2p6 when it gains the electron. And that is 10 electrons, which is the same electron configuration as neon. So the purpose of bonding, as I talked about, is really this. The purpose of bonding is, in this particular case, because lithium gave up its electron, it ended up as the same electron configuration as neon. I'm sorry, as helium, which is a noble gas. And fluorine picking up the electron ended up as the same electron configuration as neon, which is also a noble gas. And that is the whole point of bonding. Everybody wants to be, as we talked about, isoelectronic with a noble gas, which basically means has the same electron configuration as a noble gas. So the way lithium can do it here is by losing an electron, becoming positively charged, fluorine gaining an electron, becoming negatively charged, and it's that positive negative attraction that holds that together. So let's take a look at another example here. Actually, let's take a look here. Again, what is holding that together is that positive and negative attraction, absolutely no sharing of electrons, as I've been talking about, and that is what is classified as an ionic bond. Transfer of electrons, positive cation, negative anion, opposites attract. That attraction does get stronger as the charges get larger, so like a +1 and -1 is not as held as tightly as a +2 -2 attraction, or a +3 -3 attraction is much tighter or stronger in that sense. Let's take a look at another one here, calcium oxide. Again, if we look at calcium, calcium is group number 2, which means it should have 2 valence electrons. And if you write the electron configuration for calcium, it is argon 4s2. And that these 2 electrons are the valence electrons in calcium. And if we hook it up with oxygen, which is group number 6 on the periodic table, it's got 6 valence electrons and an electron configuration of 1s2, 2s2, 2p4. What's going to happen in this case is calcium is going to give away 1 electron there. Now, if you take a look on your periodic table where calcium is number 20, 19 is potassium, and back here at 18 is argon. So when calcium gives up that 1 electron, it moves it to potassium, which is close to the noble gas, but not really a noble gas configuration. So it's not going to lose just 1 electron. It needs to lose 2 electrons, which will now take it back to argon's configuration. And when it does so, the calcium, because it lost those 2 electrons, will now become positively 2 charged. The oxygen will gain those 2 electrons. And become negatively 2 charged. And again, the positive 2 here and the negative 2 here is what's going to hold that together. And that again is an ionic bond. And in terms of electron configuration, the calcium loses these 2 electrons here, which means it ends up with 18 electrons, or argon's configuration. The oxygen gains those 2 electrons right there where it has room, and it ends up as 1s2, 2s2, 2p6 in that particular case. And that is now going to be 10 electrons, which means it now has achieved the same electron configuration as neon. So again, in this case, calcium needs to lose 2 electrons to excuse me, to get to the noble gas configuration. Oxygen gains those 2 electrons to get to a noble gas configuration. Everybody really happy because they're at that noble gas configuration. Question on those 2 ionic compounds and how they are formed. Now, let's take a look at, let me actually go here. Let's take a look at what would happen if we took calcium which has our argon 4s2, and put it together with our fluorine that we saw earlier, which had our 7 valence electrons, and our 1s2, 2s2, 2p5. So same thing's going to happen here. The calcium is going to lose an electron to our fluorine. But as I just mentioned, that is only going to take it back to potassium, which is not good for calcium because he wants to get to argon. So he has 1 more electron he needs to lose. But clearly in this situation, this fluorine will now have 8. It cannot take any more electrons. And that is why in this case, we need not just 1 fluorine, but we actually would need a second fluorine to gain the electron here. And when that second fluorine gains the electron, what's going to end up happening is calcium will now be able to lose both of its electrons and become positively 2 charged. And we will end up with 1 fluorine that gained 1 electron and became negatively 1 charged. And we will end up with a second fluorine that gained 1 electron and ended up with a -1 charge. So if you remember, we just talked about naming, and when you take something, calcium with a +2 and fluoride with a -1, when we put it together, the proper formula is CaF2. And the real reason for that, other than the simple answer of you need to get it to 0, is we need the 2 fluorines in order for all these guys to get to the noble gas configuration. So that's really why when we were talking about ionic compounds and we were putting positive guys and negative guys together, And the simplest way to get to 0, the reason we do that is really for this reason here. That allows everybody in that ionic compound to properly get to the noble gas configuration and be stable. And that is because in this situation, again, no sharing of electrons here. What is holding that together is the +2 and the -1, but argon will now get to, calcium will get to argon's configuration by losing these electrons. Each of the fluorines will gain 1 electron, which will take it to neon's configuration for both of these guys. So all 3 of these guys, by losing and gaining electrons, have now reached noble gas configuration. And that really is the reason why when we're talking about ionic formulas and putting them together to get 0, that is really the purpose of that, is to allow everybody to get to noble gas configuration and be stable. As was before, if we didn't balance it out, calcium would not be able to reach noble gas configuration without the second fluorine there. And that's why when we put them together like this, and we did with naming, you want to equal 0, because ultimately that's what you're doing. When you balance it out to 0, is you're getting everybody to the noble gas configuration when they're bonding together. Question on ionic bonding, how to draw it, how to show it. Yeah, it's a little bit different with calcium hydroxide, but it would be it's kind of it's the same idea. How the hydroxide is kind of covalently bonded, and it's not exactly the same situation here, but because what you have when you have these 2 guys together is you actually have an ionic compound, but this guy here is actually sharing electrons. So these guys are actually sharing electrons covalently. So they're actually bonded together with 8 electrons. So it's got, something like this. It looks something like this. So it's not exactly the same sort of situation. It's already has sort of the electrons and stuff like that in that situation. So it's more when you'd have these sort of individual guys together. If you had something like, say, let's do magnesium, which is group 2, and let's do nitrogen, which is group 5. 1, 2, 3, 4, 5, right? So in this particular case, magnesium, right, will lose 2 electrons. So one will go over there and one will go over here, right? And when it does lose that, it will become Mg2+. But if you just keep track of what the nitrogen just gained, you have this nitrogen that has this, and this. It's actually still short one for nitrogen actually to get the 8. So we need another magnesium, right, that has 2. And this guy will go here, right, and get that guy filled up. So that will fill this guy up, right? And total, this guy gained 3 electrons, right? So he has a -3 charge. But now we have a problem with the second magnesium. He cannot get to neon's configuration because he wants to lose 1 more, which means we need another nitrogen to begin with. So he's got to lose 1, but that's only going to give him 6 electrons. So we actually need 1 more magnesium with 2. And he will go 1 and 1 more there. And if we count up my big mess that I made here, we ended up with 1 magnesium, 2 magnesium, 3 magnesiums, and 1 nitrogen and 2 nitrogens. And that would be why it ends up in that case. So that's why we need all those guys to get everybody to noble gas configuration in the simplest way. As you can see, if we stopped with just one magnesium, we didn't finish nitrogen. We had to keep going until we got everybody to get to 8 in that particular case. No, so carbon is group number 4, so it has 4 valence electrons. So number of valence electrons will equal the group number. So let's talk a little bit about covalent bonding, which is a little bit different. This is where we're actually going to be sharing electrons. So when we do get nonmetals and nonmetals together, what happens, because they have very similar sort of properties, they are going to basically decide to share electrons. So for example, if we take 2 hydrogens together, these 2 electrons here will count for the hydrogen on the left, and these 2 electrons that are being shared will count for the hydrogen on the right. And these 2 hydrogens were started with 1 electron each. Because they're both hydrogen nonmetals, will actually end up sharing those electrons. So you can represent it with the 2 dots. You can represent it with a line. One line represents the 2 dots, or a pair of electrons. And this, when we are sharing electrons, is what's known as a covalent bond. In this case, when we have the 2 electrons being shared equally, which is what we would expect here, what you essentially have are the electrons attracted to the nucleus of one hydrogen, but they're also attracted to the nucleus of the other hydrogen, and that sort of locks them together in place. So they can't really escape. So there's kind of that equal attraction here. We know there's going to be equal attraction here because essentially they're both hydrogen. So one hydrogen is going to pull the electrons just as strongly as the other hydrogen will pull it back the other way. And this type of bond is what's known as a covalent bond when we share electrons. And when we actually share electrons equally, it is what is known as a nonpolar covalent bond. So this is what is referred to as a nonpolar covalent bond. And that is the equal sharing of electrons, is basically what that is. It's the equal sharing of electrons. So why is 2 important? If you look on the periodic table, this is hydrogen. The next element is helium, which is number 2. So in order for hydrogen to be happy, it just needs to get to helium. So hydrogen should only, I'll say it one more time, only have 2 electrons, never more than 2 electrons. So when you draw hydrogen, it should always be on the outside. It should look something like this. Or if you want to use the dots, it should never have dots around it. So if you draw hydrogen like this, just put the X, it should not have dots. If you double bond hydrogen, put the X, it should not do that. If you triple bond a hydrogen, it should not do that either. Hydrogen pretty much can only do that because it just needs 2 electrons. Everybody else, as we'll talk about, needs 8, but hydrogen just needs those 2. And it's very common. People go crazy with hydrogen. They just keep on throwing electrons on there and all that kind of stuff. So what holds us together, different than an ionic bond, again, is actually that sharing of electrons. So those negatively charged electrons are attracted, again, like I said, to the nucleus, which is positively charged in both of those atoms, and it sort of locks everybody into place. Fluorine is another example here. Again, fluorine is group number 7, which means fluorine here will have 7 valence electrons. And another fluorine will have 7 valence electrons. And again, because they're both fluorine, they're both nonmetals, these electrons here are going to be shared. And what we will end up with is fluorine that looks like this, where you could draw it like so. And if you count the fluorine on the left, it has 2, 4, 6, 8 electrons. Count the fluorine on the right. Also has 2, 4, 6, 8 electrons by sharing electrons. 8 electrons on the periodic table in terms of valence electrons is our noble gases. So each of these achieve noble gas configuration by sharing of electrons. And again, you could represent the bonding electrons with a line if you want. and the dots on the outside. So these are both two ways you can represent that. Now, when we do draw this, there's two types of electrons. The ones on the outside, they're these dots where there's no other element present. These are what are sometimes called non-bonding electrons, also known as lone pairs. People still call them lone pairs. And oddly, the ones that are involved in bonding have a special name. These are what are referred to as bonding electrons. So those are bonding electrons there. Non-bonding electrons are dots. Whenever you draw a Lewis structure, you should always show both of that, the bonding and the non-bonding electrons. So a Lewis structure is showing those bonding and non-bonding electrons. Again, only the valence electrons are shown, as they are the only ones that are involved in bonding. And again, you could show the bonding electrons with a line or dots. I personally use lines, but you can use dots if you want. But you should show, again, all the bonding electrons and the non-bonding electrons. And we will stop there for lecture for today. Any questions on any of that stuff there? Okay, so make sure you type here in the chat. Those that have discussion, we will discuss. I haven't had Monday discussion in a while, so we'll have Monday. As of now, the test is scheduled for next Wednesday. I will let you know. I think it's probably going to be moved to the following week. So we will see for sure on Wednesday and see where we're at. But I think right now it's scheduled for next Wednesday. And like I said, it probably will be moved, I think. So I'll let you know for sure on Wednesday. Other questions on that? Yeah, the homework will still be due on exam day, whatever day that is, either next Wednesday or the following week. All right, I'll see everybody for discussion. That has discussion in about 5 minutes or so. Those that have lab, have a good rest of your night. We'll see you on Wednesday and stuff like that. And again, make sure you do put here if you haven't done so. You're welcome.